All right, we'll just try that. So that was wonderful. Thanks so much. I'm Alex Heuschen from Nijmegen. And my question would be, have you checked the epigenetic clock in people that carry large clones of clonal hematopoiesis? So we see that some apparently healthy individuals sometimes have clones that spread for whatever, 80% of the blood cells. And there is some new studies that indicate that they may be aging prematurely or have some other inflammatory effects that indicate that their biological age may be advanced. So I was curious whether you checked their genetic clock.
Yeah, so we have, you probably know better than me, but it's known as clonal hematopoiesis of indeterminate potential, or age-related clonal hematopoiesis. And there are two papers that have shown that this is very much associated with epigenetic aging. You can do a Google search on that topic. And then there was a striking finding, which was the following. If a person has this chip phenotype, meaning a mutation in a DNMP or TET enzyme, and but their epigenetic age is not accelerated, then their mortality risk was normal. Conversely, people who have these mutations, the chip mutations, and their epigenetic age was accelerated, they were at a drastically elevated risk of mortality and even heart disease. So there's a wonderful paper that shows that epigenetic clocks actually allow us to stratify patients with these chip mutations.
And related, was it also stratified for clone size? So I can imagine that the epigenetic clock, if it's only present in 5% of cells, may not show the result or may not be measurable accurately, while if you have a clone of whatever 20% enlarged, you may be able to see it. Was that checked?
No, it was not checked, not at all. So the study I mentioned was based on the Framingham Heart study and several other large cohorts, and I don't think they looked at that. They just looked at mutations. But yeah, exciting question.
Hi, I'm Hilger Ropers from Berlin. You mentioned these well-known studies where linking mice, old and young, would increase the lifespan of the older ones while decreasing the lifespan of the younger ones. So, to the best of my knowledge, you will know better, the molecular basis of this has not been understood, is it? And then, but then you mentioned actually this paper from Belmonte, that one with the Yamanaka factors, where they instilled, I think, the 4 Yamanaka factors for some time, month, I think, and then in the end it turned out that they were rejuvenated. So the question is, do they have a role actually in this effect also of ligating mice and then deligating them and so forth? And finally, of course, for someone like me, I'm almost 80 actually. So is there hope actually for any rejuvenation here?
Absolutely there's hope. Your question about the molecular understanding, honestly, I don't have any insight, I mean, many people are working on it. They're trying to isolate proteins and peptides that could explain this effect. There were high-profile publications on that. There are companies that try to look at the ingredients of young plasma that could explain this effect. I would say there are some insights, but whether there's a connection to the Yamanaka factors, I don't think anybody has ever looked at it.
Okay.
When it comes to human anti-aging interventions, I honestly can only tell you boring things. Exercise, eat your vegetables,
Thank you very much.
Andreas Römer from Passion Technologies. I wonder whether, since you can redesign any array for any CPG island of any species easily, have you done a comparative study of your selected CPG islets from mycelium versus a leader method, so meaning immunoprecipitation of methylated cytosines versus unmethylated. And compare how well this clock will work versus your clock.
Yeah, unfortunately, I have not done these studies. I seem to remember there's a collaborator, Benny Matsui. I think she did a comparison, and I think she liked this technology you just mentioned. I think that it worked very well in her hands. But yeah, I haven't done this comparative analysis.
Because it's basically orthogonal to your methods, so therefore it would be nice.
So the data from the mammalian methylation consortium will be released to the public. Actually, many of the data are already public on gene expression omnibus, and so anybody can do these comparative studies. We released a lot of mouse data and many other species already.
Thank you.
Hans Temple, Human Genetics Cologne. I would like to ask whether it is possible, because we model a lot human disease aging associated diseases in cell culture with human iPSC-derived neurons, for example. And there it's very difficult to accelerate maturation and also aging so that we can actually model these diseases. We were quite successful with impairing proteostasis, for example, by messing with the ubiquitin system or by damaging mitochondria. But these are all just tricks, right? We can kind of damage the cells so that they show age-like phenotype. But we have this one gene, like this one proteinuria gene or a genetic intervention that actually accelerates aging and would result in a fast track, like increase in the epigenetic clock.
Yes, at some point I had a grant on that topic. What interventions accelerate the age or the maturation, of cells in a dish? And I have to say I failed at that, so I think it's a hard problem. As you said, the obvious things are progerin, but I think I showed you some data that overall that idea, let's say progerin and the lamina, really has only a weak effect, at best a weak effect. My best intervention right now is really Down syndrome. I know that because I looked at fetal retina with Thomas Reed in University of Washington. And so Down syndrome really does accelerate epigenetic age, even in cell culture, in the organoid models. But when it comes to disrupting mitochondria, we get mixed results. So I showed you some results from Ken Raj. Certain interventions sometimes disrupting mitochondria accelerates epigenetic age, but really not always. Sometimes these experiments fail, so it's a mixed bag with mitochondria. But yeah, beyond that, if any of you know an intervention how to age young cells, I would love to hear about it. Cell passaging accelerates some of our clots, but not a lot in fibroblasts. Wouldn't it be nice if you passage fibroblasts and it accelerates epigenetic growth? It has a weak effect. It ages them maybe by 3-4 years, but not by decades.
And you can't use it in post-mitotic neurons. But okay, you just keep using it.
I mean, people use epigenetic clocks in post-mitotic neurons, So, and there was a publication on these 3D organoids, the brains, where it's Dan Geschwin's group at UCLA, so they published a paper that showed that yes, epigenetic clocks can be applied to these 3D brains, and yes, clocks apply to neurons. But how to age them? I would say Down syndrome, That's my best answer at this point.
Thank you.
So we have time for one more or two more questions, please.
Hi, my name is Stephanie from Ulm. What I would like to try to do here is a neutral question, and maybe naive, but Do you know companies that are selling polymerase to make people younger? If so, what do you think about it?
Polymerase? What is it?
Polymerase, the enzyme for
I don't know such companies, and I really don't have any opinion on that.
Yes, obviously I'm very curious to know your opinion on that, but I guess your presentation already showed that that it doesn't influence really much in the fact, so I wouldn't expect it very good conclusions, but I saw some, how to say, not film, but kind of a film about it, in which the person has good results, but also obviously there's a higher risk for cancer. But I can give an example if you would like to search later. I have one name, it's TA65, for example. That would be a product that is being sold. Anyone can buy.
Questions?
Okay, yeah. If people do Google searches on various supplements that affect the clock, you will find there was another publication, alpha ketoglutarate. Apparently there was some evidence. Then I mentioned briefly phase 1 study from Greg Fahey. I think a lot of these studies are very preliminary. They require validation, so just be cautious. And as you said, many anti-aging interventions come with a risk. There's always the risk of cancer, particularly when it comes to this interrupted reprogramming with the Yamanaka factors. That's on everybody's mind. But yeah.
Thank you.
Yeah, thank you. I think we have to close this session, and I really like to thank Steve again for his excellent talk and sharing his new insights with us. So thank you very much.